Good evening, and welcome to the Moreau Lake State Park Astronomy program, in conjunction with Adirondack Skywatchers. Tonight, we're going to explore night sky photography, the art of capturing the beauty of space. We'll start with a simple approach to capturing the Moon or Milky Way using nothing more than a digital camera, tripod, and flashlight, as we use for this image of the Milky Way taken here at the park. Then we'll look into ways to employ that same digital camera, now mounted on a telescope or its own astrophotography mount, to capture images of the planets and deep sky objects. Finally, we'll look into cameras specifically designed for astrophotography, including those that can capture high-definition still images and movies, and the use of filters specifically designed to capture the heavens, producing images such as these magnificent Hubble images. We'll conclude our presentation with an overview of the software required to turn a ho-hum image into something spectacular. So sit back, make yourself comfortable, and enjoy the show. Before going any further, you need to do an experiment to determine how long an exposure you can take before stars start to show star trails due to the Earth's rotation. This maximum exposure time is dependent on the lens, sensor size, and the number of photoreceptors on your sensor. Simply set up your camera with a wide-angle lens and tripod in a dark location, pointing the camera south toward the horizon, yet still taking in the sky. Set a low ISO, perhaps 400 or less. Open your lens to near its lowest f-stop, its widest aperture. Set your camera to manual focus and focus on infinity. Set your exposure to manual and your shutter to 6 seconds. Now record the ISO, lens aperture, and focal length on a piece of paper. Take a photo using a remote release or shutter timer and record the image number and shutter speed. Increase your shutter to 8 seconds without changing anything else and take another image, again recording the image number and shutter speed. Continue to do this until your shutter is at 20 seconds. Download the images onto your computer, increase their contrast to make the stars pop, and look at them closely. At which shutter speed did you first start to see star trails? In essence, the elongation of round stars, particularly near the corners, into what appear to be ovals. Your minimum shutter speed is that of the previous image. Any shutter speed slower than that will cause star trails. Write this down and keep it for future use. You can also do the same experiment at multiple ISOs and at multiple focal lengths, again noting the point at which each combination produces star trails. At this point, you are ready to shoot the Moon or Milky Way and to capture images with or without star trails. There are several keys to successful night sky photography with an interchangeable lens mirrorless or digital single lens reflex camera. First, for any good night sky photography, a dark sky location is critical. Light pollution, as shown here above Los Angeles, is a growing problem everywhere. Even here at the park, where much of our sky is dark, you can see the glow of Glens Falls and South Glens Falls on the northern horizon, and that of Saratoga and its malls to the south. Second, a rock-solid mount for your camera, such as a good tripod and the use of a remote shutter release or timer, are key. Shooting with your mirror locked up on a DSLR is also advised, as your exposures will be long, and any camera shake will result in blurry images. Third, shoot in RAW, not JPEG, and do so at a lower ISO so that you don't introduce additional noise and have more leeway in developing your images. If your camera has a long exposure noise control, you may want to turn it on, although this will double your exposure time, as your camera takes a second exposure of equal length with the shutter closed in order to capture noise and subtract it from your original image. When shooting the Milky Way, use a wide-angle lens focused near infinity to capture a broad vista and limit the impact of camera shake and star movement. Add an interesting foreground such as water, trees, buildings, mountains, etc. that provide context to the sky. Often you will need to light these objects with a flashlight, what we call light painting, as we did with the boats in this image shot here at the park. When shooting the Moon, a a telephoto lens is needed to provide detail. A short telephoto lens, perhaps in the 70 to 140 millimeter, is often ideal to capture the moon and foreground elements, while a long telephoto lens allows you to zoom in on lunar detail. Shooting planets and deep sky targets with a camera mounted on a tripod is nearly impossible due to their relative image size and dimness. To shoot the Milky Way, we used an ISO of 3200 and an exposure of 20 seconds on a 14 millimeter lens set at f2.8. We were able to employ such a high ISO since the camera was a professional model that offers very low noise. This may, however, give you a starting point for your own foray into shooting this iconic target. Astrophotography is a matter of trial and error, so expect to try various ISOs, shutter speeds, and apertures until you hit upon the right combination for your camera and lens, all the while taking into account your minimum shutter speed found in our earlier experiment. You'll note that in this image from the park, the stars are clearly starting to trail from left to right, emphasizing the fact that we exceeded our minimum shutter speed. For capturing images of star trails, everything we discussed to this point still holds true, except we now want to exceed the minimum shutter speed. The length of the star trails is directly proportional to how long your shutter is open. Often, exposures of 30 minutes to 2 hours are used. To do this, it is likely you'll need to use the bulb setting on your camera and lock your remote shutter release button down for the period of time you wish for your exposure, then unlock and release the remote shutter release button to end the exposure. To employ longer exposures without star trails, you can either mount your camera piggyback style on a telescope or use an electric mount designed specifically to hold a camera for astrophotography. In both cases, the mount will rotate the camera across the sky at the same rate your target moves across the sky due to the Earth's rotation. This not only allows you to use longer exposures, but also longer telephoto lens without creating star trails. If you have access to long telephoto lenses in the 800mm plus range, perhaps using a teleconverter to extend the focal length of your longest telephoto lens, planetary photography is now in your range. But to really shoot the planets as well as deep sky targets, you need to mount a camera at the focal plane of the telescope. This will provide the wonderful light gathering of the telescope's large aperture with a magnification of its long focal length and the mount's ability to track your targets. The simplest way to accomplish this is to remove your telescope's eyepiece and insert a T-mount, or to use your telescope's secondary port to attach a T-mount. Then attach a T-mount adapter specific to your camera in place of your camera lens and couple the T-mount and the T-mount adapter together, thus mounting your camera to the telescope. Now, focusing the telescope also focuses your camera. For the serious astrophotographer, a camera designed for astrophotography is a must. Due to the long exposures required for dim objects, heat builds up in the sensor, resulting in high amounts of noise in the captured image. Mission-specific astro cameras have advanced cooling systems incorporated in their design to minimize this noise, sort of like a mini refrigerator built into the camera. They also incorporate a very sturdy flex-free mount to your telescope, so as the scope slowly rotates to track your object, the cameras will not move or flex in relation to the telescope's optics. Finally, these cameras also offer a computer interface, allowing you to automate the entire process of taking your image. Some astro cameras capture only single still images, while others are capable of also taking movies by capturing a series of images and converting them into movie files. Some astro cameras can also act as a guide scope, with a small built-in computer and software that constantly analyzes the image and sends messages to your telescope's mount to make small corrections to keep the target object centered in the camera, while others rely on external guide scopes to perform this task. Even the best telescope mount will slowly drift during exposures of 20 minutes or more, and if you are shooting dim objects, such as nebulae, your exposures may run several hours per night and spread over several nights. Astro cameras may be color or black and white. In a color camera, Each photoreceptor in the camera's sensor has a small filter, either red, blue, or green, placed in front of it. The camera then averages a set of adjacent photoreceptor values to come up with a measurement of color and luminosity at each point. So in a color camera, the number of megapixels the sensor has bears little relation to the final image. A 20 megapixel camera might really only have 6 to 8 megapixels of resolution due to this averaging of photoreceptor values. When using a black and white astro camera, however, we employ a filter wheel. The wheel contains a set of filters, perhaps a blank spot, a red filter, a blue filter, and a green filter. When using a filter wheel, each photoreceptor is now recording one color of light per image. So the image contains the full resolution of the sensor. Your 20 megapixel sensor now delivers a 20 megapixel resolution image. With the filter wheel in place and controlled by the same computer that is driving your telescope mount, the guide camera, and the imaging camera, we implement a pre-planned shooting sequence. The telescope slews or moves to the target we selected. The filter wheel's electric motor turns the wheel until the right filter is in place, the camera is turned on, and the shutter opened. The guide camera corrections are transmitted to the mount to keep the target centered in the camera. The shutter is then closed at the end of the exposure. Then the data is sent to the computer for later development. For dim objects, the camera may be instructed to take 20 or more exposures with each of the several filters, automatically advancing the filter wheel as needed, resulting in perhaps 100 images or more being captured for any given target, all done automatically while you slumber in your bed. The next morning, you can then develop your images by assigning specific colors to each of the filters used in your captures the previous night, perhaps the famous Hubble palette used in this image, and then stack your images. Image stacking allows you to mathematically align these many captured images into a stack and finally adds them together. Thus, dim objects are made brighter, and noise, which tends to be random, is nearly canceled out by being averaged with other images in the stack which had no noise at the same location. Nearly all images coming directly from your camera will look terrible. They will always appear to have a strange color cast, a lot of noise, no true blacks, no bright whites, and any colors present will appear muted. In general, regardless of what photo editor you use, we correct that color cast, often by simply altering the white balance. Then we increase contrast by pushing your blacks down using your black point tool and your whites up using the white point tool. Next, we remove as much of the noise as possible without losing stars or making the images too soft. Finally, we increase color saturation. These steps alone are usually enough to result in an image you can be proud of. While many people still rely on Photoshop for image development, and tools such as Deep Sky Stacker for image stacking, there are literally dozens of highly powerful astronomy software packages, including Nebulosity, Sequence Generator Pro, Starry Night, The Sky, PixInsight, among others, that play a role in automating the entire process. When integrated, they are capable of automating a complete observatory, including opening and closing your dome or roof, powering on your telescope and related equipment, shutting it all down if lightning or rain are sensed, taking your images, and subsequently processing them. A discussion of all of these tools is well beyond tonight's presentation. To learn more about them, and astrophotography in general, pick up copies of Sky and Telescope or Astronomy magazine. Before we adjourn, we thought we'd share some wonderful images, not from a multi-billion-dollar space telescope program, but from one of the Adirondack Skywatchers members, Bill Frederick, an amateur. These images will give you some idea of what is possible from a simple backyard observatory. We hope you've enjoyed this introduction to astrophotography and that you'll join our staff and astronomers as they demonstrate their approach to capturing night sky images. we'll be showing other presentations that cover an overview of our universe and how to select a telescope and mount. We hope you'll come back soon to Moreau Lake State Park to learn more about astronomy. And until then, clear skies to all.